Hello students, today we will do topic 6.7, which is energy consideration, a quantitative study. Now here energy consideration means, again we come back to the U-shaped experiment where a rod PQ was placed on a rectangular frame or U-shaped frame, and the rod was moved in a uniform magnetic field. The uniform magnetic field was perpendicular to the plane of the frame, and velocity was perpendicular to the magnetic field. And when we moved this rod with a constant velocity, we assume that it is moving on a frictionless surface, or there is no friction, so we assume there is no loss of energy. Now we will prove that if there is no loss of energy, where the energy has gone when we moved a rod PQ on this frame. So actually when we moved a rod PQ on a frame, we did some mechanical work. We spent some energy. Energy can neither be created nor destroyed. So where our mechanical work or mechanical energy is gone, this mechanical energy is responsible for the induction. It means our mechanical energy was converted into an electrical energy, because we know the current flow through this rod, or the current flow in a loop. And later on, this current was dissipated in the form of heat. So with the help of formula, we will prove that whatever mechanical work we did to move a rod PQ on this U-shaped frame, that is converted into an electrical energy, and later on it is dissipated in the form of heat. Now what were our conclusion when we did this experiment? The first conclusion, or the derivation, or we arrived at a conclusion that when this rod is moved, the EMF induced is E is equal to BVL. And then we applied, this was from the Faraday law, we obtained this formula, and then we applied the concept of a Lorentz force, where we found that when this rod is moved, one end of the rod becomes positively charged and the other end, P rod, becomes negatively charged. That was the motion of the charge take place inside the rod, and as a result the current flow in a direction from PQRSP. So this was a loop in which the current was flowing. This current is an induced current. This current was a induced current. So current was produced because the potential difference was created between the two ends of the rod, and as a result the current was induced, or EMF was induced. Now this happened till we do the work, that is we moved a rod on the frame. Now if we assume that the resistance of this rod is small r, let us assume that the resistance of the rod is r, small r. We neglect the resistance of this wire, U-shaped wire, that is PS, SR or RQ. We neglect the other resistance, we only consider the resistance of the rod. So if small r is the resistance of rod PQ, then induced current I is equal to E upon R, that is the Ohm's law. So I is equal to E upon R, so it becomes BVL upon R. Now this current start flowing immediately when we start moving the rod. So as soon as you start moving a rod, with the velocity v, say towards left, the current is induced or the current flow in the loop in the direction PQRSP. This happened immediately. So immediately as I start doing the work on the rod, or if I pull from this side, or if I push a rod towards left, the current is induced. And according to the formula, the current induced should be equal to BVL by R, where small r is taken as a resistance of the rod PQ. Now, if I keep on doing this work, that is, I am spending the energy, that is my mechanical work, I will find out how much work I did in the form of a formula. But when I start moving this rod, it is like a current carrying wire or a current carrying rod is moving in the magnetic field. The current carrying rod is moving in the magnetic field. And if you remember, if a current carrying rod is moved in a magnetic field, or if a current carrying rod is placed in a magnetic field, then there is a force acting on it, which was given by the formula F is equal to IL cross B. So as soon as the current is induced, when current is induced, then the force acting on current carrying rod F is equal to IL cross B. So this additional force comes into the picture. Now when it will come into the picture? When the current starts flowing in the circuit or in the loop, or you can say in the rod. How much current is flowing? That is BVL upon R. Now if I apply the cross product here, let us find out the direction of this force. This force is not a Lorentz force. The Lorentz force was responsible for creating the potential difference, that is, the Lorentz force act on the charge moving in the magnetic field, due to which the current was induced. So who is responsible for this induction? That was the Lorentz force which acted on the rod, that we did in the previous lecture. Now as soon as we start moving this rod in the magnetic field, the current is induced, and when the current is induced, it is like a current carrying wire or a rod is placed in a magnetic field. Now let us find out the direction of this current. So if you remember, this was the length of the rod L, and the direction of the current here is like this. So inside the rod, this is the direction of the current. So if I take this as a direction of the current, that is, the current inside the rod is moving from P to Q. So if I apply the screw rule, the direction of the current in the rods, let us assume this is point P, this is point Q, the current is in the downward direction, and the magnetic field is inward. So this will be the situation. Current is in the downward direction, magnetic field is in. Then the screw rule. So it is L cross B. So L, this is your L cross B. So if I keep this two pen like this is my B, this is my direction of current. So my thumb is outward here. Now the actual situation is like this. So where is the current direction of this force? It is opposite to the direction of the motion of the rod. That is, this force acting on the rod is in this direction. That is, if you cannot use a screw rule, simply L can be written as minus J cap. That is, current is going in the downward direction. Magnetic field is inward. So minus j cross minus k, that is equal to j cross k. And what is j cross k? I. So what will be the direction of the current along the x-axis, or we can say opposite to the direction of the motion of the rod. This force is known as Lenz's force. This force is known as the Lenz force. And what was the Lenz force in the experiment of Faraday? When we move a north pole or the north of a bar magnet towards the coil face behave like a north pole, means it opposes the motion. And how we learned कि पास आए तो आने नहीं देना और जाए तो जाने नहीं देना. So Lenz's force should always oppose our motion. And if it does not oppose, we assume the theory of contradiction. Then the law of conservation of energy is destroyed. So energy law should be obeyed. So the work is always done against this Lenz's force. So by common sense also, this force should be opposite to the direction of the motion. And therefore, in order to overcome this force, I have to do the mechanical work. So the situation is like this. When the rod is initially placed, this rod was placed on U-shaped frame. This is how we started the experiment. No current is flowing. As soon as you start pushing the rod, or from this side pulling the rod towards left side, the current is induced. But at the same time, the current is induced due to Lorentz force. But as soon as the current is induced, the Lenz's force comes into the picture, which opposes the motion or the direction of the motion of the rod. And in order to overcome this force, we have to do the mechanical work. So it is like this. If any body is placed on the surface of the earth, how much force act on it? mg, that is the gravitational force or the weight of a body vertically downward. Now if I say you pick up this body to a height h, or you pick up this body from the surface of the earth, so what should be the minimum force applied by you? So the minimum force applied by you in the upward direction should be equal to mg. So your force applied against the gravity should be at least equal to the force of gravitation. So this is the case here, how much work I should do. And remember, here the work should be done in such a way that the velocity is constant, or you can say the acceleration should be 0. Otherwise, there is a dissipation of a heat, or there is a loss of energy. So we assume frictionless, and the work should be done with a constant velocity, or acceleration should be 0. So this force is opposite, and this force is called Lenz's force. So when current is induced, then the force acting on current carrying rod F is equal to this, and it is opposite to the direction of motion of rod PQ, and it is called Lenz's force. It is called Lenz's force. So this force comes into the picture immediately as we start moving the rod in the magnetic field. What will be the magnitude of this force? Now direction is determined. So magnitude is Bill. That is equation number 3. Substituting this value of I here, so F is equal to, I substitute this value, it becomes B square L square V upon R. That is equation number 4. So this is the magnitude of the force which opposes the motion. This is the magnitude of the force which opposes the motion. It means if I want to push a rod, or if I want a rod to move in a uniform magnetic field, the minimum force applied should be this much. This is the opposing force. This is the Lenz's force. So minimum minimum force I have to apply is this much. This force is in the direction opposite to the motion of the rod. So now I will write how much power is required to do the work. How much power? So power means energy per unit time or work upon time. So power required to move rod PQ with constant velocity V. So power is equal to F into V. That is the formula for the power. So power required by us is, we substitute this F, B square L square V square upon R. This much power if you have, then only you will be able to move this rod in the magnetic field. So this is the power we have to spend. Now how this power is spent? This power is spent in the form of the mechanical energy. This power is spent in the form of the mechanical work, or you can say mechanical energy. So if I have a power of value this much, then only I will be able to push this rod or move this rod in a uniform magnetic field. Otherwise, the Lenz's force will not allow the rod to move through it. Now this Lenz's law, like this, we can say it is like a friction. When a body is at rest on a surface, there is no friction. The friction is zero, external force is zero. But as soon as you start applying, or as soon as you start pulling or pushing a body, the friction comes into picture. Now if I push a body and if it does not move, it means there is an equal and opposite force, which is a frictional force, which opposed my energy or my applied force. Now if I increase the force and the body still does not move, it means the frictional force has increased. Then a stage comes where the body is on the verge of sliding. That is, the friction give up. So what should be the minimum force you should apply? So if I say how much energy per unit time, or how much power you will spend to move this rod in a uniform magnetic field, so your answer should be this much power has to be spent. This is the power spent. This power is spent in the form of the mechanical work or mechanical energy. So this power is spent in the form of mechanical energy. So let us write this. This is power spent to move rod in the form of mechanical work. In the form of mechanical work. So I spent this much power or energy per unit time. Now where this power or energy have gone? Now I started doing the work. Again, remember the work is done with in such a way that a velocity remains constant or acceleration is zero. So if velocity is constant, acceleration is zero. This much power I have spent. Or this much energy per unit time. Power means energy per I have spent. Now where this energy has gone? Because energy can neither be created nor destroyed. So it should be either it should be converted into some another form, or it should be dissipated in the form of heat. So we did this work. Now where this energy or where this work has been dissipated. So the energy we spent is dissipated in the form of heat. Is dissipated in the form of heat. So what is the power loss? So that can be written as I square R, that is the power loss or the dissipation of the power across a resistance, and this dissipated in the form of heat is a Joule heating effect. Now this can be written as I square. So what is I? BVL upon R. So it is I square. So upon R square, and 1 R is cancelled. So B square V square upon L square upon R. This is your energy. The energy we spent is dissipated in the form of heat. It is called Joule heating effect. So we write a subscript J. So this is equation number 6. Now you compare equation 5 and equation 6. This is the mechanical work. This is the mechanical work per unit time. Power means work upon time. This is the mechanical work we did. Now why you did the mechanical work? To overcome this Lenz's force. It comes out to be this. Now we have our, what is our energy consideration is the topic. We have to prove that the energy is neither created nor destroyed. So I spent this much energy. First thing you have to keep this in mind. As soon as you start moving a rod, the Lenz's force comes into the picture. The first thing is everything take place simultaneously. The first thing is the Lorentz force act on the charges, due to which the potential difference is created between the point P and Q. As a result, the current is induced. As soon as the current starts flowing in this rod, the Lenz's force comes into the picture. It will oppose your motion. Now if you want to overcome this motion, you have to do the external work. You have to do the mechanical work. So how much mechanical work per unit time you have to do this? Now we come to the point where the work has been gone. I spent energy to move the rod. Now if there is a bulb here, if I connect a bulb here, suppose I connect a bulb here, then this bulb will glow. So I can say my mechanical work is converted into an light energy. If there is no bulb, this mechanical work is converted into the induced current, and later on, because there is no bulb or anything like this work done is dissipated in the form of heat across a resistance. But from equation 5 and 6, it is clear that, so what is our conclusion from equation 5 and equation 6? It is clear that mechanical work done to move rod is responsible. So the mechanical work done to move rod is responsible for induction, and mechanical energy is converted into electrical energy, that is induced current, and then dissipated in the form of heat. So in this experiment also we have proved that energy is neither created nor destroyed, but it is conserved. So again we have proved the validity of the Lenz's law, which states that the current is induced in such a way that it opposes the motion that has produced it. So again the change in the flux is responsible for the induction. After induction or after the induced current, the Lenz force comes into the picture. In this case the Lenz force is in the form of BIL bill, or this force, you have to remember, is acting opposite to the direction of the motion of rod. So I have to spend energy. So my external force should be at least equal to this. So here this is my external force, but its magnitude is same. And I moved the rod with a constant velocity v. So this is the power required to move the rod. And if the power is less than this value, you will not be able to move a rod. Similarly, you will not be able to lift a block if your work done against the gravity is less than the gravitational force mg. So this is the power I spent to move a rod. Now there is no bulb, so this much power or this mechanical work is converted into an electrical energy, that is induced current, and later on dissipated in the form of heat to verify whether same amount of energy or power is lost. So we applied the formula I square R and the formula comes out to be equal. So this is the external work, mechanical work done, and this is the dissipation of the energy or the power. So energy is conserved in this experiment also. Now induced EMF produce a induced current. So current was induced because there was a potential difference between the 2 points of the rod. Now let us see whether there is some relation between the induced EMF and the charge, induced charge. So definitely if EMF have a relation with the induced current, there should be some relation between the induced EMF and a new term which will be called as a induced charge. That was the induced charge. P was in this experiment, P was negatively charged and Q was positively charged. So that was a induced charges. Now we know that according to Faraday law, the magnitude of EMF is equal to change in magnetic flux with respect to time. That is the time rate of change of magnetic flux. Now we take an example of this U-shaped experiment only. If small r is a resistance, then induced current. So induced current I is equal to, or first I write E is equal to IR. This I can be written as delta Q upon delta TR. So if I compare this two equation, the time rate of change of magnetic flux is equal to delta Q upon delta T into R. So delta T and delta T on both the side is cancelled. So what is delta Q? This delta Q is equal to the change in the magnetic flux divided by the resistance. So this is one important formula of an induced charge. So induced charge depends on the change in the magnetic flux and resistance. Remember, induced charge is independent of the time. So whether the current flowing in the loop or the circuit is for any time, for whatever amount of time the current is flowing, the induced charge will not change with respect to time. And also the charge should not be changed, otherwise the law of conservation of the charge will be destroyed. So charge can neither be created nor destroyed. So the charge in the loop or in the circuit or in any experiment of this Faraday's law, it will remain independent of the time, but it depends on the change in the magnetic flux, that is final flux minus initial flux divided by the resistance of the rod or wire in an experiment. So remember induced charge formula, and at the same time you remember the induced charge is independent of the time. So this is again the energy consideration. We have seen that in any experiment involving the induction of the charges or induction of the current or induced EMF, the energy is conserved. Have a nice day.